Hello everyone, this is my presentation on my interpretation of how to prove the Saccheri and Legendre theorem. I hope I'm pronouncing those correctly. Before actually proving this theorem, I want to address that there are three assumptions for neutral geometry. The linear pair theorem, so if two angles form a linear pair, then the sum of their measures is 180 degrees. Vertical angles theorem, vertical angles are congruent, and the crossbar theorem, if ABC is a triangle and D is a point in the interior of angle BAC, then there is a point G such that G lies on ray AD and line BC. It's interesting that we can prove the Saccheri theorem in neutral geometry because you don't need the assumption of the parallel postulate. The first theorem that I used is the exterior angle theorem, which states the measure of an exterior angle for a triangle is strictly greater than the measure of either remote interior angle. Here I have provided the proof of exterior angles theorem along with a diagram. So the proof goes as let ABC, that is not where I wanted to start, ABC be a triangle, and let D be a point on ray CD such that they are opposite, such that it is opposite of BC, and let E be a midpoint of AC. And this is given by theorem 3.2.22. And then if we choose F to be a point on BE, such that BE is congruent to EF by the point construction postulate, then given by vertical angles theorem, BEA is congruent to FEC. So hence, if their angles are congruent, therefore their triangles are congruent by side angle side theorem. Then, by definition of congruent triangles, we see that angle FCA, there we go, up there, and BAC are congruent. Now that we have proven that the triangles are congruent, we need to prove that the exterior angle is larger than the interior angle. So since F and B, F and here's B, are on opposite sides of AC, and BD are on opposite sides of AC, so that must mean that F and D are on the same side of AC by the plane separation postulate. Then if we use theorem 3.3.9, we see that A, let me change my color, A and E are on the same side of CD. So here's CD. And then E and F are also on the same side of CD. So by the plane separation postulate, A and F are on the same side of CD. So if we use the definition of angle anterior, it places F to be on the interior of A, that was not supposed to go that long, ACD. We see that it's on the interior. So hence, angle DCA, so that's the one I just drew, I'll try it again, oops, is greater than angle CFA. And this is given by the betweenness theorem for rays. Therefore, angle the measure of angle DCA is greater than the measure of BAC. The next theorem I used a lot was the alternate interior angles, and it states if L and L prime are two lines cut by a transversal T such that in such a way that a pair of alternate interior angles is congruent, then L is parallel to L prime. We will suppose that there is a point D such that D lies on L and L prime by the RRA hypothesis. If D lies on the same side of T as C, then angle A prime, B prime, and B is an exterior angle for triangle B prime, B, and C. So here we have that triangle. Excuse me, I said that and read that wrong. So it'd be B prime, B, D, so here's that triangle. And then we see that B prime, B, and C is a remote interior angle for the same triangle in orange that I just drew. It shows that it is a contradiction to the exterior angles theorem I had proven just in the last slide. So in the case where D lies on T, this should say B. I'll fix that. Then the angle of B prime BC is an exterior angle for, no, not for, and A prime B prime B is a remote interior angle for triangle B, B prime D. Okay, so this should say A. I apologize. But this is another contradiction, and since D must lie on one of the two sides of T by the plane separation postulate, the RAA hypothesis is rejected and the theorem. So the next three are lemmas that are used multiple times in the Saccheri theorem. And this lemma is 4.5.3, which states if triangle ABC is a triangle, then the angle measure of CAB plus the angle measure of ABC, this should say is less than 180 degrees. Once again, here I have the proof and a diagram. So if we have triangle ABC, A, B, C, okay. To prove that the angle of CAB, so this angle right here, plus the angle of ABC, so this one, is less than 180 degrees, we need to find a point on line AB such that B is in the middle of A and D, so we have D over here, and then the angle measure of ABC, so ABC, so that orange one right there, woo, plus CBD is equal to 180 degrees, given by the linear pair theorem. Then the angle measure of CAB is less than the angle measure of CBD by the exterior angle theorem. Therefore, if we add the angle measure of CAB plus the angle measure of ABC, it would be less than 180 degrees. Here we have lemma 4.5.4, and it states if triangle ABC is a triangle and E is a point on the interior of segment BC, then the sum of triangle ABE and the sum of triangle ECA equals the sum of triangle ABC plus 180 degrees. The proof goes as the following. So we let triangle ABC be a triangle and let E be a point on the interior of B and C. And to prove that the triangle sums of these two angles is equal to the triangle sum of ABC plus 180, we need to prove that these are all equal to each other. Ooh. So first we have triangle ABE. So A, B, and E plus the triangle of E, C, and A. So E, C, and A. Basically the two triangles I had split in ABC in half. So now those measures plus angle measure of EAB. So we have E. Oh, sorry about that. EAB plus angle ABE. Plus angle BEA. So all three angles in triangle ABE. So then we're going to take angle CAE plus angle ECA and angle AEC. I hope I said that correctly. And given by theorem 3.310, we see that E is on the interior of angle BAC. So the angle measure of EAB plus the angle measure of CAE equals the angle measure of BAC by the angle addition postulate. So then, in addition, we see that BEA and plus the angle measure of AEC is equal to 180 degrees by the linear pair theorem. Therefore, we see that the sum of ABE and the sum of triangle ACA equals the angle sum of BAC plus the angle sum of ABE plus the angle sum of ECA plus 180, which then equals the sum of triangle ABC plus 180 degrees, and we see that by using algebra and the definition of angle sum. Our third and final lemma is 4.5.5, which states if A, B, and C are non-collinear points, then there exists a point D that does not lie on line AB, such that the sum of triangle ABD equals the triangle sum of ABC, and the angle measure of the one of the interior angles in triangle ABD is less than or equal to 1/2 of triangle sum CAB. So this lemma is very important for proving the Saccheri theorem because this diagram is very similar to the Saccheri theorem diagram, which you will see in 2 slides, and it will help put into perspective and a visualization of how much the lemmas and the theorems I had proven before all become connected. So to start the proof, we see that A, B, and C are 3 non-collinear points, and we want E to be a midpoint on segment BC. So we see that here. And this is given by theorem 0.3.2.22. And then we let D be a point on AE, on ray AE, such that E is in the middle of A and D, and AE and ED are equal to each other by the ruler postulate. So we see that here. Then the sum of ABD, so A, B, and D is equal to the sum of triangle ABC. So that goes this way. So it's the two triangles that overlap each other. So now we see that either the angle measure of BAD, so this guy, is less than or equal to 1/2 of angle BAC. So this is this entire thing. Or we can have the angle measure of ADB. So ADB is right here. And that is less than or equal to 1/2 of BAC. So this one down here as well. So since angle AEC and angle DEB are congruent by the vertical angles theorem, we see that triangle AEC and triangle DEB are congruent by side angle side theorem. Alrighty, I'm going to erase this, get a little chaotic. So if we apply lemma 4.5.4 twice, this is the theorem I had just proven in the last slide, we see that triangle ABC, the sum of triangle ABC is equal to the sum of triangle ABE plus the triangle AEC minus 180. Furthermore, we also see that the sum of triangle ABD equals the sum of triangle ABE plus the triangle of DEB minus 180. Then the triangle sum of ABD equals triangle sum ABC. So to see furthermore, by using the protractor postulate, the sum of BAE plus EAC is equal to BAC. Hence, the angle measure of EAC is less than or equal to 1/2 of BAC, or the angle EAC is less than or equal to 1/2 of angle BAC. Then we can see that the angle measure of EAC equals the angle measure of ADB. Finally, we made it. The Saccheri Legendre. I apologize, I cannot pronounce names. This theorem states that if triangle ABC is any triangle, then the angle sum of ABC is less than or equal to 180. So we finally made it to the proof. I proved this by a contradiction, so I let triangle ABC be a triangle and that it was also greater than 180 degrees. So we say that triangle ABC equals 180 degrees plus a epsilon of degree, where epsilon is a positive real number. So we can choose a positive integer n large enough that 2 to the power n times epsilon of degrees is greater than angle CAB by the Archimedean property of real numbers. By using lemma 4.5.5, which is the lemma I had just proven in the last slide, we see that triangle A1B1C1 such that the sum of that triangle equals the sum of triangle ABC, which is this triangle and this triangle. We know that this angle is then 1/2 of this whole triangle, and applying the lemma a second time gives you this triangle, this yellow triangle right here, I will outline in green, which is 1/2 of the original triangle. So it's half of this one, but it's 1/4 of this one. If you keep applying this lemma a total of n amount of times, it yields that the triangle AN, BN, CN is equal to the sum of triangle ABC, which is equal to 180 plus epsilon in degrees. So then we can see that any of the triangles that we create of triangle AN, BN, CN have measures less than or equal to 1/2 n times the angle measure of CAB, and that is going to be less than epsilon. Thus, the sum of the other two angles is greater than 180 degrees. But if we go back to lemma 4.5.3, this is a contradiction, so we must reject the RAA hypothesis, and the proof is complete.